Welcome back. In our last video, we introduced the example of Anna playing skee-ball, and we saw what happened to the mean and standard deviation of this discrete probability distribution of the scores she gets on her skee-ball rolls if we mess with this random variable. We can find the original mean and standard deviation, but we could also add or subtract a constant value to each of these. And this is how it would change the mean and standard deviation. If we add a certain amount, the mean goes up by that amount. If we subtract instead, the mean gets subtracted by that amount. So essentially, whatever you do to the random variable, the same thing happens to the mean. For the standard deviation, if all you're doing is adding or subtracting a constant, the standard deviation doesn't change because you're not changing how spread out the data values are. If instead you multiply or divide by a number, the mean still is just multiplied or divided by that number. So the mean does exactly what you would expect. But you will see there is a little bit of a change I've made from what we said in the last video. I've changed that formula slightly. If you're going to multiply or divide the values of the random variable by a number, the standard deviation can never be negative for a distribution like this. So you are allowed to multiply by a negative number to make all these values negative. But the scalar would still have to be positive for the transformation, right? So even if you're multiplying by a negative number, if a is negative, the standard deviation would still be positive, so you just take the absolute value of that scalar. So now let's put both of those ideas together. So let's say that the original points are doubled and then 50 is added to that doubled value. How would this affect the mean and standard deviation? So we're putting the two ideas that we went through in the last video together. And again, I'd like you to try and figure out on your own without calculating what would happen to the mean and standard deviation. And it would be really cool if you could come up with formulas for the mean and standard deviation that would work for this. Here's the table for what you would have for the distribution of points if we double these original values and then add 50 to them. So we'll range from 70 to 150. Again, the probabilities are exactly the same. The probability that 2x plus 50 equals 70 is 0.32, so on and so forth. So we're trying to find the mean of 2x plus 50 and the standard deviation of 2x plus 50. I'm going to use the shortcut because I already know the formulas and I would know how to write that out. So we go to our calculator. We've typed in those 2x plus 50 values in L1, probabilities in L2, stat, calc, 1-bar stats. Our list is L1, our freak list is L2, just as before, and we calculate. It says x bar is 97.6. We know that's the population mean mu, so it's 97.6. And the standard deviation, 25.3. So as you may have guessed, the mean of 2x plus 50 is twice the original mean, 23.8, plus 50. It's exactly what we would have thought. So, turns out the mean of ax plus or minus c, so we're multiplying or dividing and adding or subtracting at the same time, is going to be the same thing as taking the original population mean, multiplying or dividing by the same number, adding or subtracting the same number. For the standard deviation, you'll see it's still only twice as big as the original. And again, it's a little different due to rounding. So again, the plus or minus c doesn't affect anything, right? It's only the fact that we doubled the scores that is affecting how spread out the data values are. So the standard deviation of ax plus or minus c. Again, we're going to bring that a out front, the number we're multiplying or dividing by, and take the absolute value in case it's negative. And then we're just doing that times the original standard deviation. The plus or minus c doesn't change anything. So these are the most generalized formulas that we're going to have here for calculating the mean or the standard deviation of a single random variable. But what's going to happen if we introduce a second one? Okay, now we're going to make things a little more interesting. Let's say the arcade's having a doubles tournament. So Anna invites her friend Erin to play with her. So this is Erin's probability distribution for her roll scores for the original point system. So this is Anna's distribution for the original points 10 through 50. This is Erin's. Anna, her random variable is x, Erin is y. So you can compare and contrast these two. But what I want you to do right now is I want you to take Erin's probability distribution and find the mean and standard deviation. I hope you took the time to calculate the mean and standard deviation yourself. What I ended up with, the mean of Erin's roll scores is 31.8 and her standard deviation is 14.6. I could have actually typed all this in, or I could have typed this into, let's say, L3 in your calculator and this into L4. You might want to keep these in L1 and L2. Sorry if you got rid of that, you might want to put it back in there. And then do one var stats on L3, L4 to get those values there. Okay, so for the moment you may have been waiting for, let's put their scores together. And the reason why we might want to do that, let's say for the tournament, Erin's and Anna's scores will be added together. So given the standard scoring scheme, just 10 through 50 for each lady, what are the mean and standard deviation of their combined scores per random roll? Now, we could try to construct a probability distribution table for their combined scores. And in fact, I will show you what that looks like. And I will, by showing you that, tell you you don't want to do that. That is going to take a long time. We are going to want to try to come up with formulas such as these, but not for messing with a single random variable, but for combining them both. So what I'd like you to think about is, if we want to find the mean of their two scores added together, what would be a really easy way that you think that could work? Because as we know, the mean usually does what we expect. If we multiply it by something, the mean's multiplied by that thing. If we add or subtract something, the mean gets added or subtracted by that same thing. So if we're adding x and y together, the mean, well, if we're adding x and y and trying to find the mean of it, how do you think that works? The standard deviation may be a little different, but you could still try and come up with what you think it might be. If you want to try and come up with the probability distribution table, I'm not going to stop you. This is going to be a pretty short video, so you've got time if you want it, but it's a lot. So I want you to at least try and guess what the mean and standard deviation would be based on what we know about each individual lady's distribution. So go ahead and figure that out now. Come back when you've got it. So here are the mean and standard deviation of the two scores added together. You may have been able to reason why the mean of x plus y should be 55.6. It is as simple as taking the mean of Anna's score and the mean of Erin's score and adding them together, which is really neat. You'll see the probability distribution table up there. It's nasty. You might not even be able to read all those little numbers. I promise they're there. Why is it so complicated? Well, if we add these two together, we have to think about all the possible things that could happen. The lowest score that you could get adding them together is if Anna gets a 10 and Erin gets a 10. The probability of both of those things happening would be 0.32 times 0.14, which is 0.0448. Next worst thing would be them getting a combined score of 30, but there are two ways of that happening. Anna getting 10 and Aaron getting 20, or Anna getting 20 and Aaron getting 10. The probability of that happening is 0.32 times 0.28 plus 0.27 times 0.14. You can see how nasty it gets. Especially in the middle here, like there are lots of different ways for them to get a sum of 50 or 60. You don't want to have to do that. You can do it. I did it, but it took me maybe about 10 minutes. And I think I messed up at least once. My probabilities didn't add to 1. So you don't want to have to calculate the probability distribution of the sum of two random variables, ever. You want to skip straight to the formulas. How am I going to know, based on these two distributions, what the mean and standard deviation look like? For the mean of x plus y, it's as simple as the mean of x plus y is the mean of x plus the mean of y. Super simple. Okay? You don't have to show all of that work. You could just say this and then put the numbers in. Okay? For the standard deviation, if you tried to guess what it might be, I doubt you came up with 19.3. You may have thought, well, I'll just add the standard deviations together. 12.6 plus 14.6. But that's too big. But those of you who are eagle-eyed might notice I added what the variance of Anna's scores were and what the variance of Aaron's scores were. If you add the variances together, the variance of x plus y is 372.32. That is 159.56 plus 212.76. So if you add two discrete random variables together, there is no direct relationship between the standard deviation of the sum and the original standard deviations. But there is a relationship between the variances. The variance of x plus y is equal to the variance of x plus the variance of y. This is one of the more difficult things for students to wrap their head around, is that if you're only messing with one random variable at a time, we usually are dealing with the mean and the standard deviation. But when you start combining random variables together, like x and y, the relationship is with the variances, not the standard deviations. And the reason for that is, if this relationship exists, which it does, where the variances are related in this way, if you take the square root of all the variances, it no longer works. If we take the square root of this to get the standard deviation of x plus y, that's going to be smaller than if we take the square root of these separately. To get the relationship in terms of standard deviations, you would have to take the square root of both entire sides at once. But I think it's easier. Chances are, if you need to use a formula like this in a problem to get an answer, you'll be given the variances. So if you know this is the relationship that exists and you have both of these, just add those variances together, take the square root of that sum to get the standard deviation of x plus y. And there is one more thing I want to say in this very short video. Wow. And that is, there has to be a certain relationship between these two variables for these formulas to be valid. And that is, when we calculate this probability distribution table, which I didn't expect you to do, by the way, but in order to calculate the mean and standard deviation, this does have to be able to exist. The way that I did this was, I said that the probability of this and this is multiplying them together. But that only is the case for certain random variables, right? And the probability of A and B is only the probability of A times the probability of B if the variables are independent of each other. So for these formulas to be valid, the random variables have to be independent of each other. Okay, so if we're talking about combining random variables together and finding their mean or standard deviation, you need the fact that they are independent, the random variables. If they are not independent, then all of these probabilities are off, because it's not as simple as A times B. That calculation is a little different, right? So the way this comes up could be on like a multiple choice, or it could be a free response, where they give you some kind of scenario where you have two random variables and you're asked whether the variance of x plus y is equal to the variance of x plus the variance of y. And you would have to say no if the two variables they give are not independent. So say you're like pulling marbles out of a bag without replacement, right? Those are not independent events because every time you take a marble out, the probabilities are changing. So if your two random variables are based on something happening without replacement, you can't do this necessarily. Unless there's a condition that we talk about a little later in the next unit. Anyway, the variables must be independent. And that is the key to these formulas here. We are almost done with this general idea of discrete random variables and how we can mess with them. We've now learned how to calculate the mean and standard deviation for pretty much anything involving just one random variable. Given the original distribution, you can find the mean and standard deviation. If we add, subtract, multiply, or divide, or do some combination of those things, you know how to calculate the mean and standard deviation for a single random variable. You now also know how to calculate the mean and standard deviation of two independent random variables. But these distributions were using the original scoring scheme. What happens if they're not? That's really the last step in this. How do these formulas change if instead of x plus y, we add, subtract, multiply, and divide stuff? That's what the next video is going to be about, and that one should be relatively short as well. So that will be the end of chapter 15. So your chapter 15 homework, you can probably tackle almost all of it at this point. And there will be another quiz after the next video, and there will be a progress check. Multiple choice part B is going to be due after that next video. So if you haven't looked at those two things, the chapter 15 homework and multiple choice progress check part B, take a look at those. The less you have to do it once, maybe, the better. Because if you wait until the last second, you're going to hate me. I don't want that. So, take a look at those. We have one last video over this example. We'll still be dealing with Anna and Aaron. I'm not going to pull the rug out from under you. And we'll see you in that next video.